All right, let's jump right in. Today, we're taking a magnifying glass to Elon Musk's $25 billion Terafab project. Announced with massive fanfare at Austin's Sehome power plant, this is a proposed semiconductor fabrication complex designed to output 1 terawatt of AI computing power. But instead of getting swept up in the sci-fi grandiosity of galactic civilizations and orbital networks, we're going to view this strictly through the uncompromising lens of semiconductor supply chain experts. We need to see if the financial and physical realities actually add up. To really ground this audit, we need a solid reality check. And honestly, there is no better baseline than this thought from NVIDIA CEO Jensen Huang. Pay close attention to the word he uses here: artistry. Manufacturing chips at the 2-nanometer process node using extreme ultraviolet lithography isn't just about pouring concrete and buying expensive machines. It relies on decades of accumulated, highly guarded institutional knowledge. Matching the yield rates and defect controls of a giant like TSMC is historically profoundly difficult. Okay, let's dive into this. Here is our expert audit checklist. We'll start with the silicon supply crisis, then we'll audit that $25 billion tag. After that, we'll hit the terawatt scalability problem, talk about poaching the semiconductor ecosystem, break down the fabrication timeline trap, and finally ask, is this a historic milestone or a costly mirage?
First up, Section 1, the silicon supply crisis.
So, why take on this nearly impossible task in the first place? Well, it all comes down to a massive looming bottleneck: 20 gigawatts. According to Musk's estimates, if you take every single fabrication facility currently operating on planet Earth, they collectively produce about 20 gigawatts of AI compute annually. For Tesla, that is just a drop in the bucket. They estimate that 20 gigawatts represents a mere 2% of the compute they're going to need at full scale. Think about a future with 10 million Optimus humanoid robots running around, each needing powerful, localized processing, not to mention millions of autonomous cybercabs. The current global supply chain simply cannot manufacture chips fast enough to meet that projected demand. If this bottleneck isn't solved, the timeline for that autonomous future essentially hits a brick wall.
Now, the allocation of this proposed output is really fascinating. You would naturally think a facility located at Giga Texas would be built primarily for cars and robots. But no, a staggering 80% of this factory's output is earmarked for space. Specifically, the radiation-hardened D3 chips for SpaceX's orbital AI satellites. Only 20% is terrestrial, meaning the AI-5 and AI-6 chips for Tesla's cars and Optimus robots. This reveals a highly unconventional business model, basically trying to capitalize on the unlimited solar energy and natural thermal cooling of space to completely bypass terrestrial data center grid constraints.
Moving on to Section 2, auditing the $25 billion tag. Musk has publicly stated a budget of $25 billion for Terafab, with an ultimate massive goal of producing 1 million wafer starts per month. But let's put our supply chain expert hats on and look at the financial disconnect here. Bank of America Securities estimates that to build a capacity of just 100,000 wafers, which is exactly 1/10 of Musk's goal, it would actually cost over $60 billion. Furthermore, look at TSMC's very real-world expansion in Arizona right now. That is costing them $165 billion. So, when you view this through the lens of actual global fab costs, the $25 billion stated budget looks incredibly, almost impossibly light. And the reality check gets even wilder. Achieving that ultimate 1 terawatt goal isn't just a matter of building a single $25 billion factory. According to analysts at Bernstein, producing a terawatt of compute at the leading edge would require the equivalent of between 142 to 358 new fabs. That equates to a capital expenditure not of billions, but of $5 to $13 trillion. That actually exceeds the entire current global semiconductor manufacturing base combined. We are talking about rewriting global industrial economics here, not just setting up a big factory in Texas.
Which brings us to Section 3, the terawatt scalability problem.
To even attempt to solve this extreme scalability problem, Terafab is trying something completely unprecedented in the commercial space: total vertical integration. Traditionally, the semiconductor supply chain is incredibly fragmented. One company designs the chip, another makes the complex lithography machines, another fabricates the logic, someone else provides the high-bandwidth memory, and yet another handles the advanced packaging and testing. Terafab wants to pull every single one of those highly specialized disciplines entirely under one roof. Bypassing the traditional distributed vendor ecosystem like this is arguably the most ambitious commercial integration attempt in tech history.
When we contrast these two operational models side by side, the financial risks become painfully clear. A general-purpose foundry like TSMC optimizes its processes across hundreds of different customers. This drives down costs through massive economies of scale and decades of painful trial and error. Terafab, on the other hand, is a captive, vertical model. It is hyper-optimized for just two proprietary workloads, the D3 space chip and the AI-5 terrestrial chip. Because it entirely lacks broader market scale and decades of process maturity, analysts expect Terafab's wafer costs to be 30 to 50% higher than TSMC's. Because remember, financial capital alone absolutely does not instantly buy high yield rates or fixed defect densities.
Section 4. Poaching the semiconductor ecosystem. So, if you lack process maturity, how do you get it? Simple. You buy the people who already have it. Tesla literally cannot operate a 2-nanometer EUV fab without the world's most experienced engineers. So, they've launched a highly aggressive recruitment campaign straight into the absolute heartlands of semiconductor manufacturing, Taiwan and South Korea. They are explicitly targeting TSMC and Samsung employees with over a decade of experience hunting for hyper-niche expertise in gate-all-around, FinFET, and backside power delivery network technologies. This right here is a critical supply chain vulnerability. You can buy the machines, but you simply cannot run them without poaching the human capital that knows exactly how to tweak them.
Next up, Section 5, the fabrication timeline trap.
Let's measure these stated execution goals against actual industry-standard ramp-up times. The project was officially confirmed in January 2026 and launched in March. Musk's aggressive target is to hit volume production of the AI-5 chip by 2027. But building a fab, installing the tools, running pilot wafers, identifying defects, and qualifying the entire process for volume production takes years. Bank of America strongly grounds this timeline in reality, estimating that massive-scale production is realistically pushed to 2029 or even beyond. And honestly, the gap between 2027 and 2029 in the AI race is an absolute eternity.
And as experts, we have to look objectively at the historical counter-evidence. The supply chain industry very clearly remembers Tesla's 2020 battery day, where promises regarding the 4680 battery cell took years longer than stated to actually materialize at scale. We've also seen the Dojo supercomputer project face a cycle of cancellations and revivals, and the AI-5 chip itself has faced major delays just to reach the tape-out phase. Grounding this cosmic ambition in industrial reality means we have to acknowledge a track record of severe delays on these types of megaprojects.
Finally, Section 6, historic milestone or costly mirage.
We've looked at the massive capital disconnects and the enormous physical hurdles. So what is Terafab? Let's steelman both sides. The skeptics look at the data and say this is pure hubris. Building advanced chips at the 2-nanometer node requires an established, highly specialized ecosystem, trillions of dollars for scale, and decades of operational artistry that simply cannot be bought overnight with a $25 billion check. But the believers point to a totally undeniable history of disruption. Tesla and SpaceX entirely rewrote the economics of orbital rockets with the Falcon 9, and auto manufacturing with gigafactories. Here's the balanced expert assessment. Even if Terafab wildly misses its 1 terawatt goal, successfully spinning up even a limited pilot fab to produce their own consumer tech chips would meaningfully de-risk their supply chain and stand as a historic industrial milestone.
Which brings us to the ultimate question. The compute bottleneck is incredibly real, and the stakes for global AI dominance couldn't possibly be higher. But can raw ambition, backed by a fraction of the necessary capital, truly compress decades of delicate semiconductor physics into a single gigafactory? Or is the $25 billion Terafab destined to crash hard into the unyielding realities of the global supply chain? It is an unprecedented gamble, and the entire tech world is watching the blueprint. Thanks for joining me on this explainer. And remember to always keep questioning the numbers.